Yes, I've started the recording. Essentially, we'll be redoing what we did in the last class towards the end of the last class. I realized I had rushed quite a bit on few topics, so we'll do them again, and then we'll maybe tomorrow in the next class we'll again continue with receiving antennas. I'm also thinking that we can have an tomorrow's class we can have on revising some of the topics from the previous class if there is any specific topics that we want to discuss. So so today again we'll be doing module 5, which is the antenna arrays, and we'll discuss the general uniform linear arrays. We did the two element arrays like properly and rushed towards the end of the general uniform linear arrays. We have discussed the radiation fields of elemental dipoles, antenna patterns, and linear antennas. And from the next class, we'll start with receiving antennas. Do let me know if there is any specific topics that we can discuss in one of the classes. We have I think we have total of 12 classes with us, and this is only the fifth one, and we are almost halfway through the course. So we have quite a few time, quite we have time on our hands. So this is the textbook that we are referring to, DK Cheng, and we are doing model 5 from here, from chapter 11. And yeah, so this class will be doing the general uniform linear arrays. Just to check again, I'm still audible, right? Any issue with my network or voice? Rajeshri or Surendra, can you please confirm if I'm still audible?
Yes, sir.
Yeah, thank you so much. Okay, so we discussed the two elements arrays in the
You are
previous
audible,
class.
sir.
Yeah, thank you. Uh, so yeah, so we did two element arrays in the last class, and I just have prepared a one slide review of what we did, all the math that we did. So we had this setup for two Hudson dipoles, two elemental dipoles, which are radiating, and we're calculating the effective electric field due to these two these two elements and the array of these two elements, and this is at a distance of r naught and r1 from the elements 0 and 1. Okay, so so what we are doing is we are using the principle of superposition for electric fields, and we're trying to calculate the effective electric field at point P. So we have the electric field due to element 0 and element 1 written over here, and then we just add them at that point P. Then taking the uh, common things over here, EM is the effect of the magnitude of the electric field, and F naught is the element factor, which we have already seen in the previous classes for different orientation of the dipoles. We get different element factor, and then this is the common term. This is the E by R terms for the both the elements. Now simplifying the terms inside the square brackets, we uh, get the electric field expression over here like this, where we have replaced psi, and psi is basically beta d sine theta cos phi plus uh, psi. Uh, okay, so this is the electric field expression that we have now, and this can be like rewritten in this form, where we have the magnitude of the electric field is now given as this expression over here, where so the e power j beta r and e power j psi, these terms have like magnitude of 1, like, so they do not contribute to the magnitude, and hence we are left with the expression over here. So over here, the f theta phi term, we know this is the element factor, and the cos psi by 2 term is actually is the array factor. So the array factor basically comprises of all the effects due to the arrangement of the elements, and element factor gives the effects due to the type of element which is being used. For example, if it is an array of dipoles, uh, the orientation of how dipoles are arranged will be contributed by the array factor, and the fact that they are dipoles will be contributed by the element factor. So, for and if we replace the dipoles with, for example, patch antennas, then the array factor would remain same if the orientation remains same, but the element factor would change based on the new type of antenna, which is the patch antenna. So yeah, so these are the two terms that we have to keep in mind. And so take an example. For example, if we had two parallel z-directed half-wave dipoles, in this case we will have the element factor given as f theta like this, and then we can put this inside the electric field expression, and then we get the final electric field expression for the parallel z-directed half-wave dipole. So this would be electric field uh, at the point P due to the two half-wave dipoles. Okay, so this is all from the two element arrays, and then we had discussed a few terms like principle of superposition and the array factor in terms. So you can refer to the previous class. We had discussed them quite in detail at that time. Well, okay. So there was this example that we did in the previous class. We'll do it again just to revise the broadside and end fire configurations. So this example is from the textbook, and the example asks us to plot the H plane pattern. So let me just, okay, I forgot to correct this. So this is the H plane pattern for of two parallel dipoles for the following cases. Now we have d equals lambda by 2 and xi equals to 0, and d is equals to lambda by 4 and xi equals to minus pi by 2. So we discussed this in the last class, and one of them forms the broadside case, and one of them forms the end fire case. So we'll quickly look at that. Okay, so the array factor for the H plane, the theta would be pi by 2. So we will substitute that. Okay, so yeah, so psi is over here. We expanding the psi, which is beta d cos pi, uh, and sine, and there was a term sine theta over here. Sine theta was here. So since sine theta, where theta is equals to pi by 2 becomes 1, so that is eliminated, and then we have this term. And now we are given the values of d and this xi over here. So we substitute that, and for the first case, the array factor is this cos pi by 2 cos phi, and for different values of phi, if you plot this, we achieve something like this. And if you see, the two elements are over here and over here, and the maximum radiation is in the broad side. Okay, okay, so I enlarge it quite a bit. So this is the direction of the maximum radiation. So this is known as the broad side. This is the broad side, and similarly, if we solve it for lambda by 4 and minus pi by 2, this is the array factor, and if we try to plot this expression, we end up with something like this. So over here, the elements are over here, and the radiations maximum they maximize in this direction towards the end of the array. So this is known as the end fire. This is known as the end fire array. So these are the two configurations. So we'll start with again with the general uniform linear arrays now. I'll pause here just in case if you have any questions from broadside array, end-fire array, or the derivation that we did over here.
Hello. Hello.
Ye- Yes, yes, Surendra.
Sir, my voice is clear to you.
Yes.
Sir, I have small doubt, but that is a silly doubt. Actually, you did all E-field based expressions you took in
Yes.
the derivations. Okay.
Yes.
Why not we are not taking H field, sir?
Um, okay.
That is a
Good
small silly
question.
doubt.
It's not a silly question. It's a good question. I mean, it's kind of convention or the norm that we are doing with the fields. Also, I think we are doing derivations with mostly with the elemental dipoles, electric dipoles. I believe so. We are using the expressions from the yeah, so we started. So if you remember, when we were doing derivations for dipoles, we did two of them. One was the electric dipole, and the other was magnetic dipole.
Yes,
And
sir.
I think we did derivations for the magnetic dipoles using the H fields. Maybe uh, I'll have to cross check that. But yeah, it's kind. I think there are two answers. Maybe the one of them is I have to check that if this is it because we are doing with the electric dipoles, that's why we are using the electric fields. The other could be that this is the convention. We mostly derive all the things with electric fields, and we can always calculate the magnetic field by just the Maxwell's equations. So we always have the flexibility. Let me just verify that the magnetic
Uh,
dipoles, did we do them with H fields?
hmm. Okay, sir. Okay. Okay, sir. No problem. If possible, do you have any literature with the magnetic dipoles? Can you share in the group?
We did derive the expressions for magnetic dipoles, if I remember.
Okay, okay, sir. Thank you.
Yeah, so those are available in the recordings. You can go through them as well. Okay.
Sure, sir.
Okay. So yeah, we did derive both the electric fields and the magnetic fields for E and H for electric and magnetic dipoles. And what we did was we used the auxiliary potentials to derive these expressions. Uh, so I guess the answer would be that we can always calculate the one of the fields from the other because they are linked. So by convention, we use the electric fields. Uh, but I think I'll have to look this up if maybe there could be some other reason. Okay. Maybe I'll look that up. If I find a different answer, I'll let you know. We could also look up on the internet that why we are doing all the derivations with the electric fields. If you find a better answer, do share with the class. Uh, Anybody else with any other question? Or Surendra, do you have any other questions?
No, sir. Thank you. Uh,
Okay, so we discussed the two element arrays. We just revised what we did in the last class, and then we looked at the example again to just uh, again revise the broadside array and the end-fire array. So we'll start with the general uniform arrays again. So so till the previous slides, we had an array which had just two elements, and now we'll generalize it for an n element array. So in this case, we're considering. Okay, just let me change the pointer. We're considering a uniform linear array of identical antennas. So it's important that we keep the identical antennas because the maths would become really complex if the different elements have different element factors. Uh, and now they are equally spaced along the line and with equal current magnitude. So all of them are being fed equal magnitude of current, and then they have progressive phase shift. Okay, so these are the constraints that we are starting our constraints that we're starting with for our array, and then later what we can do is we'll see an example where we change the magnitude of the current to reduce the uh, just uh, give me a second. Yeah, sorry about that. Let's start again. Okay, so yes, so this is what the array is how this would look like. So we have n elements, all of them are separated with d separation, and the phase shifts are given by zeros, psi, 2 psi, and so on. So this is how we are arranging the array. And yeah, I was saying then so right now we are keeping them identical, equally spaced with equal current magnitude and a progressive phase shift. Um, what we can later see is that we can uh, change the magnitude of the current in different elements to achieve different like a better performance in the radiation pattern to reduce the side lobe levels. We'll see that later in the class. So this array's pattern function is a product of the element factor and array factor. So we've seen this in the two element arrays. The array's pattern function is product of the element factor and array factor. Uh, so we've seen that. Now, we'll, we'll focus on how the array factor depends on the parameters beta d and psi. So beta d is essentially based on the wavelength of the excitation, the separation between the elements, and the phase shift between the elements. So these are the factors which could help us tune our array. So the normalized array factor in the xy plane would be written as like this. So in the previous maths, if you remember, when we took the superposition of the electric fields, we all the things were taken common except the exponential terms. And in this case, and they did have a term in the denominator by r. So assuming it to be same for all the elements, this is the normalized array factor would look something like this. So we are taking things in common, and we get this expression. And if you look closely, this as discussed in last class, this is actually a geometric progression. So since we and we know the summation expression for a geometric progression where we have n number of elements. Using that, we get this expression over here. So this is the expression for the array factor. And if you and so 1 minus e power j psi and 1 minus e power j psi, and this these terms individually they can be rearranged to get the and be written as sine n psi by 2 and sine psi by 2. So let me change it to a pen. Yeah. So I think what we can do is yeah, take e power j n psi by 2 common, and then we'll have e power minus j n psi by 2 minus e power j n psi. Sorry about the handwriting. By 2. So this would be left with us if we take this thing common, and since everything is inside mod, its magnitude is essentially 1. So this is just the phase term, and what we can do is multiply divide by 2 over here, and this expression is essentially sine and psi by 2. So that's how we get the numerator. Similarly, if we take e power j psi by 2 common, if we take that common, this entire thing would convert to sine psi by 2, and again, like, we have to take this 2 common again over here. So we'll have the 2e terms again, and these 2's can get cancelled, and again this e power j and e power j terms, they are only they contribute to the phase, and the magnitude is 1. So, so if we take them outside the mod, they'll just vanish. So that's how we end up with this expression for the array factor. So I'll just pause over here and take any questions that you have with this derivation. Okay. So I hope this was clear. If there are no questions, we'll proceed. So this is the general expression for the normalized array factor, and we have sketched this expression over here. So we'll get into details of this figure in the coming slides. So this is actually this is the plot for the array factor versus the argument psi over here, and so the first peak is the main lobe, and then this is the first this is these are the side lobes. This is the first lobes, uh, the first minor lobes, and over here is these are the nulls. And now the width of this main beam is something which we'll calculate. And so there are many things that so based on the this array factor gives us essentially the radiation pattern for the array, and there are many things from the radiation pattern which are of concern to us, uh, such as the width of the main beam, the location of the first nulls, and gain and the magnitude of the first side lobes. So these things we'll see. So this is from the array factor, and now this array factor is actually function of beta d and psi, and beta d and psi, and this beta d and psi based on these, we have seen that we have either the broadside radiation pattern or end fire radiation pattern. So for both the cases, the derivations would be a little different, and also and as the phi varies from 0 to 2 pi, the value of psi changes. So essentially, what we're saying, this argument of array factor varies from, uh, if you remember this expression, psi is equals to beta d cos phi plus right plus xi. So when this uh, this varies from 0 to 2 pi, this psi term varies from beta d plus xi to minus beta d plus xi, so covering a range of 2 pi beta d. So that's what it says. So this is the and this is known as the visible range of the radiation pattern. So based on the value of this pi over here, the value of psi uh, varies by 2 pi d, 2 beta d, sorry. So 2 beta d, and this is known as the visible range. So this is just a definition for you to remember if there are any questions and exams for you to answer. And so, as this said earlier, we may derive several significant properties based on the array factor from the next slides. So the first one is the main beam direction. So for example, if we had an antenna or we had an array of antenna, so just by looking at the if for example, if we just had one Hudson dipole, right? So for example, if we had a dipole over here, so we know that how the radiation pattern would look like. It would look like a donut, and we know the where the direction max where the direction of the maximum radiation is. Similarly, if we had a patch antenna, we would know the how based on the excitation, it would be a broadside, and where would be the maximum direction, maximum uh, radiation direction. But when we make arrays, we have how would we know where the main beam direction is? And for example, if the array is something simple like this, we can solve it mathematically and get the direction of the maximum radiation, and that is the main beam direction. So based on the values for this beta d and xi, this will decide uh, where is the direction of the main beam. It could be either end fire or broadside. So let's see that. So the maximum value of the maximum value of the this array factor is when this numerator and denominator, they like this ratio is maximum, and this is maximum when the psi value is 0. So I think taking limits and stuff, if you remember, if there's something known as L naught L'Hospital or L'Hopital's rule, something like that. So based on that, we get the limits at psi equals to 0. We get the maximum of this function, and for during that, so this psi is equals to 0 is the maximum, so which implies beta d cos phi plus xi equals to 0, and this implies cos phi is equals to minus xi by beta d. So two special cases will be of importance. The first is the broadside, and in this case, the maximum is in the direction perpendicular to the array. So which so yeah. So this is, if you see, this is phi over here, and if the radiation direction is maximum in this direction like this, so this is essentially 90 degrees, right? So this is 90 degrees. So and similarly, or if it could be in this direction, so it could be minus 90 degrees. So for phi equals to plus minus pi by 2, if that is the direction of the uh, main beam, this implies this cos phi is equals to 0, which implies xi must be 0. So this for xi equals to 0, this means the main beam is in the main beam is perpendicular to the direction of the array, which implies is a broadside array. And this all so for and what does this xi equals to 0 means? It means that all the elements in the linear broadside array should be excited in phase. So xi was the progressive phase shift, right? So the progressive phase shift is now equals to 0. So there is no phase shift between these elements. So this was the phase shift, right? So xi is 0, which implies there is no phase shift. So when the array elements are excited without any phase shift, we get the maximum radiation in the broadside direction, which is perpendicular to the direction of the array. And now for the end fire array, the radiation occurs in phi equals to 0 direction, which is towards the x-axis like this. So if this is the direction of the maximum, this implies this cos phi equals to 0, or cos phi equals to 0, which implies beta d plus psi equals to 0, which implies xi equals to minus beta d. So we get the value of phase shift equals to minus beta d. And this was also seen some days back in some of the one of the examples. Okay, so I'll pause over here and take any questions on broadside array or end fire array. If there is any confusion on the things which we discussed now.
Hello, Anand sir.
Mm, yes.
Hello,
Uh,
Surendra.
yes.
This is Surendra. You are explaining about phi naught equal to plus or minus by 2. Then the array direction is in the radiation pattern is in the broadside direction, and if it is phi naught equal to 0, then it is comes to end phi direction.
Yes.
Yes. Uh, by changing the phi value only, the beam is tilted to the broadside to the end fire.
So actually, it's the other way. If we are deciding which is the broadside direction. So the broadside direction is phi naught is equals to pi by 2.
Yes.
And to get that, we are substituting that in the psi relation, this 1188. Let me just
Okay.
turn this to phasor.
Ah,
Okay.
1188 is pi psi
Yeah,
equal to
1188.
pi
So, yeah,
beta
so
d
we're
sub.
choosing where we want the maximum direct radiation, main beam's direction. If that is perpendicular to the array, which is the broadside direction, when we substitute that inside this expression, we get the value of this psi equal, xi equals
Beta.
to 0, which means there is which means if all of the array are excited in the same phase, we have the radiation in the broadside direction. And similarly for the end fire, so at the end fire means it should be towards the array, like towards the like one of the ends of the array, which means the phi value should be 0. For phi value, if it is phi value 0, if we substitute this in 1188, we get beta d, and the psi is equals to 0 because that is the maximum. So this is already 0, and now when phi is equals to 0, this 1188 gives us beta d equals minus xi, or xi equals to minus beta d. So this gives us the expression for the amount of phase shift that we must give in the array elements, so that the maximum the radiation or the main beam direction is of an end fire array towards the one of the ends.
Okay. Okay, sir. Okay, sir. Thank you.
Okay. Any other question?
Sir, one more small doubt.
Yes.
Can you give one example? For example, if it is a patch antenna, okay, we are
Okay.
making linear array, okay.
Okay.
The if theta pi theta e is around 30 degrees, okay, how it convert into the end fire means broadside beam convert into end fire? Is there any example or any literature available with you?
Um, I'll have to look it up, but I think if you use CST or HFSS, it should be possible for you to design it. You'll have to see how to feed the different elements. So let me try to draw. So you're saying that, for example, if we have patch antenna like this, patch antennas, right? Something.
Yes, sir.
So there are different elements. So,
Yes,
and we know if we feed them like with equal thing, that will give us a broadside radiation.
yes, yes,
And you want it to be an end fire.
yes,
So in this case also, I think this math should work. This if we make the phase shift equal to beta minus beta d, this should work. Or otherwise, start with this, and then we can start tuning the phase shift value among different the elements. So there is, if for an end fire array, there has to be progressive phase shift, and how much that phase shift would be, you can get an approximation from here. This B point end fire array, and then you can tune that phase shift between the different elements. Since I have not designed myself any end fire array using a CST or HFSS, so I'm not sure how to give progressive phase shifts in that, but I am sure there would be some tutorials available on YouTube if you search for them.
okay, sir. Okay, sir. Thank you, sir.
Yeah, you're welcome. Okay, so if there are no more questions on this, we'll proceed. So the second point is the first thing was the main beam direction that we have discussed. The second point is on the null location. So the null location is also very important because, for example, if you have two devices that are communicating, and it is important that their main beam uh, align. So which will essentially mean that there is good connectivity somehow. Uh, but if these two devices, for example, this device is communicating in this direction, has a main beam in this direction, and the other one has a main beam in another direction. But so it's fine as long as there is some radiation in this direction. But if there is a null in if there is a null where this device's main beam is, so let me redraw this. Uh, so there was this device which has a beam in this direction, but the other device's main beam is in this direction and it has a null in this direction. So it will essentially mean this the antenna has very poor gain in this direction, and its reception will be poor. So it will rely on the gain of the other antenna, which is trying to communicate with it. If there is sufficient other if there is path loss is much greater, then you could lose all the signal strength. So it's very important that we know where the null is. So let's try to calculate how where the null would be in this particular case. So to have a null, which it implies that the array factor has to be 0, which means this expression has to be 0, and this is 0 when the numerator is 0, and the numerator is 0 when sign, the argument of sign is equals to plus minus k pi by 2, where k would be 1, 2, 3, they belongs to the integers, right? K belongs to integer, or okay, so we have included plus minus over here, so k belongs to natural numbers. So in this case, we will have the null locations, and it is obvious that the corresponding null locations in phi are different for broadside and end fire arrays because of different values of psi and different value of xi and psi. So this 1188, this expression 1188 is very important. So we see the expression for psi, even for different values of um, uh, phi, since the value of the xi changes for broadside and end fire. This implies that um, the null locations would be different for end fire and broadside. So for different phase shifts, the null locations would change. So again, this is very important to note that, for example, if you're trying to make an antenna whose main beam is in certain direction, uh, so for zero phase shift, we saw that it was in the broadside, and for a certain value, it was towards the end fire. And so this implies that changing the phase shifts value can help you tune this uh, main beam's direction between broadside and end fire. So you could tune this towards any direction, and this also means that you can tune the null locations. These null locations could also be tuned by changing the phase shift values, which is these xi values. Okay, I'll pause again over here. Just if there are any questions on this, the position of the nulls.
Hello. Hello.
Yes,
Sir.
yes, tell me.
Sir, one another small doubt. Is there any relation between the array factor as to the gain?
Array factor to the gain. Yes,
Yes.
there is. So if you remember, the beginning of the class, we said that the radiation pattern is
Yes.
dependent upon the element factor and the array factor. So if we remember correctly, the radiation pattern is something like this. For example, let's say, so the antenna will have different gain in different directions, right?
Yes.
Yeah. And similarly, the element factor, for example, if you're taking Hudson dipole, so it would be like isotropic in one of the H planes, right? So it essentially means it has equal gain in one of the planes. But based on the array factor, how we arrange it, it could mean that the array factor is something like this. So these two patterns, there is something known as principle of superposition of patterns. I think maybe we discussed it in the last class, or it's there somewhere. So these two, how based on their product, is essentially how the final radiation pattern would look like. So if, for example, over here we had some certain gain, right? But in the
Yes.
array factor, this gain is very less. So in this
Hmm.
direction, the gain would become very less. For example, if
Okay.
the element factor had a very high gain in this direction, and again array factor had a uh, max good value over here, like high value over here, the product will mean that we have a higher gain over here. So based on the pattern which comes from the array factor and the element factor, we get the final radiation pattern, which decides how much gain will be there in which direction. So it does affect the gain.
Based on the
Also,
null. Yes, sir.
yeah,
You
in
given
the
the good.
locations as well.
Mm. If based on the null locations, is there
Yes.
any possibility to produce means generating grating lobes?
Grating lobes. So, okay, a new term, grating lobes, if I remember correctly, these are, for example, if this is the radiation pattern, like for example, horn antenna, right? It looks something like this.
Yes, sir.
So, yeah, so these are the grating lobes, right?
Grating lobes are equal to the north equal or approximately equal to the main lobe. These are the what you drawn are the side lobes.
Uh, I said, could you repeat that again?
Is there you said about the null locations?
Yes.
Uh, these null location, based on these null locations, is there any possibility to generate the grating lobes in the array pattern?
I mean, it, I haven't done it, but it does seem possible because based the array factor is essentially multiplied to the element pattern. So if you could engineer null locations inside the radiation pattern uh, by rearranging your array, and which means basically you are trying to modify your array factor to have different null locations in your pattern. And yes, you by varying the null locations, you could essentially engineer creating loops in your array pattern. So yes, you can do that. I'm not sure what exactly would be the process of how to introduce nulls, but I think you could find papers on this. It seems quite possible. If it has an application, it must have papers there.
Okay, okay, sir. Thank you, sir. Thank you for clarifying
Yeah.
doubts.
So yes, we can engineer null locations since the first point was on the main beam direction. So based on the direction where we want the main beam, we put the psi value and then calculate the direction of the main beam. Uh, or we could engineer where the main beam should be. Similarly, the second point, we are looking at the null locations. We're trying to calculate where the null locations would be. So based on the phase shifts, we can also engineer the null locations. And hence, if we, for example, we could introduce grating lobes inside the array pattern. So if there are no more questions on this, we'll move to the next point, which is the width of the main beam. So the angular width of the main beam between the first nulls can be determined approximately for large n. Uh, okay, so for smaller n's, for example, if we saw in the previous two-element array, we saw that the radiation pattern looked something like this, like the circles. So in this case, the width of the main beam is essentially pi, right? So because the null locations are over here, but if the beam is narrower, in this case, there is some possibility to have some angle which could give us the width of the main beam. And this is important, for example, if based on the application, like for example, if you want a higher gain, which implies this beam should be narrower, and for example, the region where we want to uh, look using the antenna is this. So we can have a more narrower beam. So what we can do is we can try to reduce the beam width. But if we want a more omnidirectional or isotropic sort of pattern, what we can do is we can try to increase the main beam width. So yeah, so this is important that so at many times we are given the beam width of the antenna, and we are required as engineers to design an antenna with a certain beam width. Now, beam width can be calculated by just taking the difference between the first nulls, and what we can. So in the previous slide, we did calculate the location of the first nulls, and so this, the first nulls where we had the value of k's, and the first for k equals to 1, we have n psi 0 1 by 2 equals to plus minus pi, which implies psi values is equals to 2 pi by n. So this is the location of the personals. And now for broadside or end fire, we'll have to calculate for both the cases. So for the broadside case, from the previous slides, we know the phase shifts should be 0, and the value of uh, phi should be equals to pi by 2, and substituting that over here, so this side term is side, so substituting this over here and then substituting the value xi and phi, this gives us cos phi 0 1 equals to cos, so this is cos phi 0 1, and yeah, substituting that, right? Yeah, what's up? So this is the location of the first null, and this is theta is essentially the location of the main beam, right? So and over here this will be pi by 2, so substituting pi by 2 over here, and this is the essentially, okay, let me just rewrite this. For example, this is broadside. So broadside radiation pattern would, this array pattern would be looking like something like this, and this is phi naught equals 90 degrees, right? And this is the first null location. So this angle is essentially delta phi, and this angle over here is phi 0 1. Yeah. 501. Yeah. So this is what, so we're trying to calculate delta phi over here, and 2 times delta phi will give us the width of the main beam for broadside array. And we know this phi naught is pi by 2, and cos pi by 2 plus delta phi is essentially sine delta phi, and this term, yeah. Yeah, we are rearranging this term over here. So xi was 0 and cos phi was psi beta by d. This is psi 1 beta by d. And now this is sine delta phi is equals to xi 1 xi 0 1 by beta d. And taking the inverse of sine, we get lambda by nd. And now we are getting this lambda by nd because this xi 0 1 is equals to 2 pi by n. So we are substituting 2 pi by n over here. Is 2 pi by n beta d. Now beta is equals to 2 pi by lambda. You can substitute that 2 pi by lambda in the numerator, cancelling the 2 pi, we get lambda by nd. So we get the width of the main beam for a broadside array as, and so the width of the main beam is actually 2 delta phi. So this will be 2 lambda by nd. So there is this line over here, so which is approximately twice the reciprocal of the array length in wavelengths. So nd is the array length, and this is 2 lambda is the wavelength. Sorry, lambda is the wavelength, and 2 lambda by nd is twice the reciprocal of the array length in wavelength. So this is something which was in the textbook, which seemed nice to read. Yeah, so I'll pause over here. This is how we are calculating the width of the main beam for a broadside array, which is 2 delta phi, and 2 delta phi is equals to 2 lambda by nd. So we did do some math and skip some of the steps. I'll pause over here, let you, if you want to write down or if you have any doubts on this, we can discuss now. Okay, so let's quickly do that again. So this was the location of the first nulls, and we get the value of psi equals to 2 pi by n for the first null. Now we are now trying to calculate the width of the main beam for broadside array, and the first null location occurs at psi 01. So this is the radiation pattern for broadside array. We have the phi equals to 0, which is the direction of the main beam, equals to pi by 2. The location of the first null happens over here, which is phi 01. Now this angle is delta phi, and okay, and so the width of the main beam between the first null is 2 delta. So if we are taking the same, this is symmetric, and this is again, this is also delta by, this is delta phi. So 2 delta phi is equals to this phi 01 minus uh, minus theta. And now using this expression, phi 01 is equals to beta d cos phi 01 plus xi, and xi is equals to 0 for broadside array. Now cos phi 01 is equals to phi 01 by beta d, and now cos phi 01 is actually theta plus delta phi, theta naught plus delta phi. Uh, Naught plus delta phi. I'm mistaking somewhere, but anyways, yeah, cos phi 0 plus delta phi, and now cos phi 0 is essentially is pi by 2, which implies this is sine delta phi. This was sine delta phi, and taking the inverse of sine over here. And if this is denominator is much larger than the numerator, we can just ignore the sine inverse term, and this is what we end up with. So the final width of the main beam is 2 delta phi, which is equals to 2 lambda by NB. So that's it for the broadside array. Now similarly for the end fire array, we again have the location of the first nulls, and we have the phase shift equals to beta d, and we have now uh, phi equals to 0. Now phi is equals to 0, it means phi 01 is psi 01 is equals to beta d plus xi over here, and this xi is minus beta d. Okay, sorry. Uh, yes, so this is minus beta d, and cos will be yeah, this is phi 01 is equals to beta d cos phi 01 minus beta d. Now we have the value of this psi from here, and we can take this beta d and beta d common. So upon taking common, we have cos phi 01 over here minus 1, and this psi term 2 pi by n, and not uh, yeah. So first we keep the psi term by beta d, and now then substitute the psi value to pi by n over here, and we end up with minus lambda by nd. And this thing can be again simplified by expanding the exponential series for cos. So this would approximate. So cos phi 01 can be written as cos delta phi, because again this cos phi 01 is cos phi 0 plus delta phi, and cos 0 is 0. Yeah, cos 0 plus some angle is the same angle. And again, and this expression cos delta phi can, upon expansion, can be written like this. So just refer to some math textbook, you can get the polynomial expansion. And we're not taking the higher order terms because this delta phi is small. So again, substituting this back into this expression, this 1 and 1 cancel, and we end up with this minus delta phi square by 2 is equals to minus lambda by nd, which implies delta phi square by 2 is equals to lambda by nd, or delta phi is equals to root over 2 lambda by nd. So this is the expression for width of the main beam for an end-fire array. And if you compare this with with broadside, this is actually greater. So the width of the main beam for a uniform end-fire array is greater than the uniform broadside array of the same length. So if for an array of 5 elements, the width of the end-fire array will be much larger as compared to a broadside array. So that's an observation. So I'll pause again over here if there are any questions on this. Otherwise, we'll proceed with the next slides. Any questions on width of the main beam for a broadside array or end-fire array? Okay, if there are no questions, we'll proceed then. The next is the side lobe locations. So similar to the previous math that we did, again using 1189. Now the side lobe location is when the numerator is maximum. The main beam, the main lobe was, the main beam direction was when this entire expression was maximum. The side lobe is when only the numerator is maximum. So the numerator is maximum. Then when the numerator is 0, we have the null locations, and when the numerator is maximum, we have the side lobe locations. So when sine n psi by 2 is equals to 1, or when n psi by 2 is equals to odd multiples of pi, pi by 2. And the first side lobe occurs when this is m equals to 1. You have to note that for m equals to 0, there is no side lobe because it is still inside the main lobe, because the first null occurs at uh, uh, n psi by 2 is equals to plus minus pi, and we cannot have a side lobe before the first null. So I'll pause again over here. This is about the side lobe. Any questions on side lobe locations? You could also write your questions in chat if there is some audio issues. Okay. So from the side lobe locations, it's very important that we discuss the first side lobe level, because it apart from the main lobe, the next location where most of the power is uh, sent is the first side lobe level, is the first side lobe, and based on the first side lobe level, we can like decide quite a few things. So the first side lobe level compared to the main beam is the key characteristics of an array's radiation pattern, as they're typically the highest side lobes. Uh, you could have an array where this the first side lobe might not be the second the second highest, but it's usually the radiation pattern would look something like this, and the first side lobes are actually the next highest levels. And in most cases, what we do is we try to suppress this first side lobe, so that more of this power is transferred towards the main. So if we keep the side lobe levels very small, we will have more power in the uh, main beam. So let's calculate the uh, magnitude of the first side lobe level. So this written green over here, we have to minimize side lobes to focus radiated power in the main beam direction. So and since first side lobe is usually the second highest after the main lobe, we can focus on reducing the power in the first side lobe level. So this is so in the previous slide we calculated the location of the first side lobe level. So this was the location, and substituting this back in the array factor, we can get the magnitude of the array factor at that location. When we substitute this back, um, uh, we have the numerator as 1 and the denominator as sine 3 pi by 2n, and this expression is essentially so for small values of sine, we can remove the sign and just keep this thing, and this, and since would be a positive number, we can cancel them, and we have 2 by 3 pi. So this is usually the magnitude of the first side lobe level. This is mostly independent for large values of n. So all this the magnitude of this first side lobe level uh, is almost independent for large n. So this would be 0.212. So which is quite significant. Like if the first side lobe level is 1 and the so sorry, the main beam is 1, so the second beam is almost 20% power of the main beam. And one of the ways to reduce the side lobe level in the radiation pattern uh, of a linear array is to taper the current distribution in the array elements. So in this case, when we started, we said that all the elements, this 0, this 1, 2, this all the elements were receiving equal power, the equal amount of current. Sorry, the equal amount of current. But so all of them had equal current. So this meant side lobe levels to be higher. Uh, but what we can do is we can taper the amount of current in the side lobe levels in the linear array. So what we have is the first element has lesser current than the second element, and so this so on. So it means the array element at the center has the highest current, and then again the current magnitude starts reducing towards the end of the array. So if this kind of current distribution follows along the array elements, the magnitude of the side lobe level would reduce. So this is one of the ways to reduce the side lobe levels, to taper the current distribution in the array elements. I'll pause over here if there are any questions on the uh, on the side lobes and the first side lobe level.
Hello, sir.
Yes,
Uh, the side lobe levels in broadside array and end fire array, which one
yes.
gives better side lobe levels, sir?
Um, okay, so let's see. We did observe that a broadside array is narrower than, like, the beam width of a broadside array is less than the end fire. So this implies the side lobes probably cannot say with 100% certainty, but the side lobes of the broad side would be smaller as compared to the side lobes of the end fire. So the side lobes in the end fire would be larger. And did I answer your question?
Oh, yes, sir. Your answer. I understood that one.
Yes.
Uh,
Any follow-up
but
questions?
uh, any mathematical expressions for this one, sir?
Mathematical expressions. Um, yeah, I mean that would be a good assignment, no? Yeah. So I would leave this up to you. We have the expressions with us to do that. So why don't you just try with pen and paper and see if you get it? So if not, then we can discuss.
Sure, sir. Thank you.
I mean, it should follow because we have seen these main beam width of the broadside is narrower than the end fire. So similarly, and we have seen the side lobe level will have this expression. So it should follow. You should be able to do that. But we have also seen in this particular derivation that uh, you'll get the magnitude equals to, like, for large values of n, the side lobe levels power remains same. So I think okay. So I'd like to modify my answer now. So we just saw that for large values of n, yeah, over here, for large values of n, the magnitude of the side lobe is almost independent. So this and it would come out to be this value. So I think for both of them, the side lobe level would be same. It would remain same. Sorry. So it would remain same for either end fire or broadside.
Okay, sir. Thank you.
Yeah. And so there is an example in the textbook which shows how by tapering the current distribution among the array elements, we have lower side lobe levels. So this is the example. So you can refer to the textbook for the complete solution. But let's just quickly go through. So for example, if you had 5 elements, 1, 2, 3, 4, and then 5. You had 5 elements, and then the magnitude of the current that is being sent is in this ratio: 1, 2, 3, 2, 1. Sure, sorry. So this is the ratio in which the magnitude of the current is 1:2, 3:2, 1. So this is what is meant by tapering the current magnitude of the current. So this is how the current distribution is among the elements. And if you have this particular current distribution and then do the math, we will end up with an array factor looking like this. Um, so from the previous example where we had almost 20% power inside the side lobe levels, now we have only 11% power in the side lobe levels. So this is what the example tells us. Uh, so kind of do it yourself. Also for the previous question, like what will happen, how much would be the side load level for a broadside or end fire? I mean, just don't trust me or don't like or just take my answer. Just do the math yourself. You must you'll be able to, I think, get the answer. So the math would be pretty simple in this case. The problems or what I struggle with are the simple trigonometric expansions of where to use them. Mm, I'm not really good with high school mathematics. So, for example, for how the cos turns into 1 minus the argument is theta, so theta square by 2 or something. So these things don't actually come to me naturally. So I rely on textbooks. But if you are able to do these things yourself, I think you'll be able to calculate all those expressions. Yeah. So what I was saying was, if you just taper the current, the side lobe levels would reduce, and there is this example in the textbook. Um, I would recommend you go through it. So the textbook is, again, to remind you, D.K. Cheng, chapter 11. Okay. So some concluding points. So up till now, we were looking at uniform linear array analysis and assuming equal spacing, equal amplitude, and phase shifts for mathematical simplicity. Okay, so you could always have unequal spacing. Um, we did see an example of uh, tapering current distribution in the amplitude of the currents in the different array elements. And we did see some variation in the phase shift. For example, if the phase shift is 0, we have broadside radiation. If we have a certain phase shift, we have end fire. And if so, there was this. So, however, these parameters that, that we have seen, tapering, amplitude, unequal spacing, is also used in arrays, and non-constant phase shift. For example, you don't have a constant phase shift. You just excite different elements in different phases. Can improve the radiation characteristics, or such as reducing side lobes or attaining certain parameters such as grating lobes, which was suggested in the class. So those things can be achieved by varying these parameters, like by changing the spacing, you could introduce nulls. So by varying by exciting different elements with different phases, you can introduce nulls or reduce the side lobes. Additional parameters For example, if right now what we did was 1D array, but if you arrange these 1D arrays in a matrix, we can have 2D arrays, and will if and as soon as we have 2D arrays, we will have more parameters that can be tuned to achieve different radiation pattern. So, for 1D array, what we have is that have we can tune the direction of the maze. We can steer the beam in maybe in one plane, but if we have 2D array, we can steer the beam in in any direction. Similarly, so we will have more flexibility as to introduce more parameters. And But as soon as we start deviating from symmetry, which is the equal spacing or same amplitude or equal phase shift, doing mathematics will become difficult. So there are different synthesis techniques which are available in literature. So, as for example, if you take patch antennas or bow antennas or Vivaldi antennas, so there are some specific techniques which can be used to model them, and then based using that, you can do some mathematics, or you could also rely on the EM solvers for you to generate the radiation patterns and the parameters that you want to tune or design your antenna for. Now, in the previous slide, as we said, we were looking at one-dimensional problems, and we can also have two-dimensional arrays, two-dimensional rectangular arrays, which are basically arrays of linear arrays. And they can be, yeah, let me just get back to a pen. And yeah, and we did see that the radiation pattern is kind of product of the element factor and array factor, right? So if we make an array of this array, this would again be multiplied to get the final radiation pattern of two-dimensional rectangular array. Yeah, I was saying in during some on the slide that there is something called pattern multiplication principle. So if you make arrays of arrays, you can keep multiplying the array factor to the previous array, and this entire thing becomes your element factor now. So if you are making an array of an array, the this thing becomes your element factor, and now this is the new entire thing. So this will become your element factor, and then you can have another array factor multiplied to it. And from this, the another observation was that if for zero phase shift, we had broadside radiation, and for minus beta d, we had end fire radiation. So if we tune the phase, we could have radiation between the broadside to end fire, and so hence this implies that we could also scan the beam of the antenna. So essentially, electronically changing the phase shift will by using phase shifters, we can scan the main beam instead of having to rotate the like manually or mechanically move the antenna. We can just steer the beam without moving it mechanically, just by electronically shifting the phases of the excitation of the individual elements. And this introduces something known as phased arrays, which we won't be looking at in these class because it's a little advanced for this course. But if you want to go in like this, so this particular topic is in itself a subject. So there are textbooks on phased arrays. If you are interested, you can go through them. And the phased arrays are very crucial in radars and radio astronomy and other areas. So that's it for this class. So I'll stop here, take any questions from what we discussed now or from whatever we had discussed in today's class or from the previous class. I'll pause over here for a few minutes, and if there are any questions from the previous classes or previous class or this class, you can ask them now or till end the class, today's class. And I'd recommend uh, solving the examples that we did in the class or some assignments that I have given. If you get time, please. So the assignments are basically examples from the textbook. So the solutions are also there. You could also just go through the textbook and see the examples if you are able to follow them. Okay, so I guess things which we discussed now were pretty straightforward. So if there are, why did keep the annotations? Okay, I'll try to remove them. Okay, so if there are no further questions, we will just end today's class and see you guys in the next class. Thank you for joining.
Thank you, sir. Thank you.